Hello. In this video, we're going to look at some notation and vocabulary related to set theory. So in math, a set is a group of objects, which we call elements, chosen from within a universal set. Most of the time, these elements will be mathematical objects, so numbers chosen from within a universal set of all the possible numbers, or we may choose to limit ourselves for particular contexts. Maybe our universal set is only whole numbers or whatever it is. Those elements could be shapes, two-dimensional, three-dimensional. Those elements could be types of functions. So just whatever it is we're defining within a universal set that we're defining. A subset is a set formed from elements inside of another set, and the empty set contains no elements. So to give an idea of an example here, we use Venn diagrams to represent. If U represents the universal set, A could be a set and then a smaller set B of things within it. If U, for example, is the set of all numbers, A could be the set of all positive whole numbers, for example, and then B could be the set of all even numbers, and that would be a subset of the set of all whole numbers. The way that we would represent this is to say that B is a subset of A. A is also a subset of the universal set. That's always going to be true. And B would also be a subset of the universal set. So this sort of elongated C means is a subset of. To show that something is an element of a set, we use a slightly different symbol. So let's say I had some element X inside here. We often denote the elements that we're going to write inside these circles by putting a little dot beside them. So let's say I have the element X and the element Y inside of there, and let's say the element Z here, and let's say we have some other element W out here. What I can say is that, sorry, I don't need the dot here. I can say that X is an element of A. I can say that Y is an element of A. For Z, Z is an element of B, but Z is also an element of A because A is a subset of, or B is a subset of A. All of these are also elements of the universal set. W, as I've written it, is not an element of A, but it is an element of the universal set. Everything is an element of the universal set, so we don't usually bother writing it out. I could put another set in here, so let's define a set over here, which I'm going to call set C. And let's say there is nothing in that set. Well, then I could say that set C is the empty set. There's nothing in it. I can denote the elements in a set using what I call curly brackets, curly braces. So the set A, if these three elements that I've written in there are the only three elements in A, then A would be equal to this curly bracket, X, Y, Z. It's those elements. And B would simply be equal to Z. So those brackets are essential for indicating that we are dealing with a set. So they're a little tricky to draw. With some practice, you'll get it. Basically, just draw some squiggles. The relationships between sets, if they're not fully subsets, we can have an intersection of two sets. This sort of upside down U symbol right here is how we indicate intersection. It's made up of elements in both sets at the same time. And if that intersection is empty, we call those two sets disjoint. So in the bottom half here, what we've got, these are disjoint sets because there is no intersection. That occurs if the intersection of A and B is equal to the empty set. But if there are elements in both, then the intersection is elements that would be found in this overlap between the two sets. The union of two sets, so that is a U symbol, is made up of elements in one or the other of the sets or their intersection. So often in language when we say something or something, so do you want soup or salad, we mean you have to choose between the two. You can't have both. But in math, that's not what this means. In math, if I say set A is the set of people currently taking an English class and set B is the people currently taking a math class, you are in set A union B if you are taking either math or English or both of them. So in the Venn diagram, that's this entire region representing both circles and their intersection. So everything in this space. Linguistically, the intersection is related to the word and the union is related to the word or. complement of a set is all of the elements in the set that are not in A. And there are two different notations listed here. We can use A with an apostrophe, we call that A prime, or A with a bar over the top of it. So if the set A is all of the elements inside the circle, then the complement of A is everything outside of it. Together, A plus not A have to equal the universal set. This rectangle always represents the universal set. Now, there's two different things we often try to represent in Venn diagrams. We may be trying to represent the actual elements, in which case we do what I did in the first case. We can list the elements in the sets with little dots beside them. We may also just be interested in how many elements are in a set. So if, for example, I have a set A and a set B, and I'm just interested in how many elements are in them, I might write numbers inside of those sets. So we represent, instead of saying A equals, we can say NA equals, let's say, 23. That tells me there are 23 elements inside of set A. And let's say I know that there are, in set B, let's go with 31 elements in set B. Let's say furthermore that I know that there are, let's go with, in the intersection, let's say they share 7 elements. So now in the Venn diagram, what I can do is I can say, well, in the intersection, there are 7 elements. Notice I'm just writing the number 7. I'm not putting a dot in front of it. That means I don't know what those things are, but there are 7 of them in that section of the Venn diagram. For A, I'm not going to write a 23 here. That is not what I'm going to do, because 23 is all of the elements in the whole circle, which includes the 7 I've already written down. So there are actually only 16 elements in this particular section. And for B, there are 24 elements in this particular section. Because if I were to add together 7 and 24, that would be that whole circle. That's the 31 that are in B. So if I want to know how many elements are in the union of A and B, so how many elements are in A or B, from this Venn diagram, I can simply add them up. 16 plus 7 plus 24, which is 47. This formula here, the principle of inclusion-exclusion, says that I can get that same value, the number of elements in A or B is the number of elements in A, plus the number of elements in B, minus the number of elements in the intersection. In other words, minus the elements that I counted twice when I just added A and B together. So if I do this, 54 minus 7 is, again, 47. So two different ways to figure out the number of elements in the intersection. In the union. All right, let's consider some notation here and trying to figure out. In these first two, we're going to shade the section of the Venn diagram that is indicated by this notation. So right here, what we have is A, the upside down U is and, not B. So we want elements that are in A and at the same time are not in B. So that is just this region right here. Elements that are in the circle for set A, but they are not also in the circle for set B. When I have 3 sets, that gets a little more complicated. We kind of respect a similar order of operations to what we do for numbers. So I have to kind of consider what's in the brackets first. So right here, I have A or B. So remember that A or B is everything in these 2 circles that I've outlined in red here. So we'll use that information. And at the same time, C. So I am going to use a yellow highlighter first to highlight A or B, sorry. So this is A or B. And at the same time, I'll use a different color highlighter. And I want it to be in C. So I've used the blue to highlight C. I've used the yellow to highlight A or B. The green is the intersection. The green is the and part of this. So I'm going to go over that a little more thoroughly. This bit right here in green is the A or B and C. So now I'm actually going to erase. Whoops, nope, did not want to do that. Go back. Just in green, I'll fill in A or B and C. Another way that you can think of this, there is a somewhat distributive property here, because if I think of the OR as addition, so this is kind of like A plus B times C. So I can think of this as A and C. So the intersection of A and C is this part right here, or B and C, which is this part right here, and the or means I include both of them. So two different ways to come to that conclusion. And finally, given this diagram, can I represent symbolically what is shown here? So let me first sort of describe what I'm seeing. I'm seeing that these are the elements in A or B and not A and B. So elements that are in one or the other, but actually not in the intersection. So one of the things that I can do here is I can say, okay, well, compare these two diagrams. If I just look at this section right here that I'm outlining in red, that is, and I'll use blue to write down the answer, that is represented by A and not B. We saw that in our first example. The other side of it would be represented by B and not A. So those are the two individual pieces of the diagram. Since I want to include either of those two pieces, this is now an OR. So A and not B, or B and not A is represented here. One of the applications of sets that we will come back to again and again is how that applies to real numbers. Real numbers can be sorted into sets. So the universal set of all real numbers, we're going to define some subsets. And there's some notation here. If I want to represent all real numbers, we use this R. Now, I've kind of put two lines there. That's because if it was typed, we would use a bold-faced R. So in printing, we often just put a second line somewhere to show that it's bold, and we use capital letters. So capital R for all real numbers. Within that set, we can describe the set of whole numbers, or what is sometimes called the strictly positive natural numbers. So that would include, let me make sure I've got a blue pen. This would include the numbers 1, 2, 3, 4, on and on forever. The natural numbers would basically be that same set, but now I would include a 0. So 0, 1, 2, 3, 4, and on and on and on. Integers. Now, it's standard to use a Z for integers. I'm honestly not entirely sure why. In Alberta education, on diploma exams, they will use an I for integers. This is not standard anywhere else, but it does show up in Alberta education. It does not show up on IB exams. So that is not really a standard notation. But the integers are the positive and negative whole numbers. So an infinitely continuing set off to the negatives, but let's say we then -4, -3, -2, -1, 0, and then 1, 2, 3, 4, dot, dot, dot. Notice for each of these, I'm using the squiggle bracket. All right, so those are whole numbers. Rational numbers get a little more complicated to express this way because rational numbers is all the numbers that can be expressed as a fraction, as a ratio. That is where that word rational comes from, is the same root as ratio. So rational numbers, now instead of making a list inside these set brackets, I'm going to give a definition. So what I'm going to say is these are all numbers, and I'll use x. So I'm going to define x. This vertical bar means such that. So all values of x such that x can be written as m over n, where m and n are elements of the integers, and n does not equal 0. So that's a definition here. So rational numbers are all the numbers that can be written as fractions. If it can be written as a fraction, then when it's in its decimal form, that decimal will either terminate or it will start repeating. Irrational numbers, notice the notation here, that's the complement. So irrational numbers are numbers that are not rational. So any number that cannot be written as a fraction. In practical form, these are numbers that the decimal representation never terminates or repeats. And examples of these that you're familiar with would be things like pi, the square root of 2, the cubed root of 21. All of these are examples of irrational numbers. There's infinitely many more, so I can't really make a list of them. And they are simply defined by being not rational, so we use the complement notation. These number sets can all be represented as a Venn diagram, and they are essentially nesting sets. So if this universal set is all real numbers, then initially that is divided into irrational numbers and the irrational numbers. Now I'm writing it such that it looks like the set of rational numbers is larger than the set of irrational numbers. That's not true. I just need more space because we have more subsets within the rational numbers. Those two, I'm not using circles because between the two of them, they are all of the real numbers. All of the real numbers are either one or the other. Within the rationals, however, I've got my integers. Within the integers, we've got the natural numbers. And within that, we've got the strictly positive natural numbers. So some examples is obviously not a complete list. I can have the numbers 1, 2, and 3. The natural numbers, the only new element they contain is 0. The integers, now we've got things like -3, -2, -1. Within the rationals, I might have 2/3, or maybe I have 0.75, or I have, I don't know, 89/27. These are all rational numbers. Within the irrational, the same 3 examples I did above. Obviously, these are not exhaustive lists. All of these sets are infinite, so I can't really list them all. There are actually subsets within the irrational numbers as well, but they are not really relevant to us at this moment.